everyone. This is Vincent Racaniello, and welcome to Session 4 of Week 8 in Virology Part 1. In this session, we're talking about capping and polyadenylation of mRNAs. We're taking a step back in the transcription process and looking at how the ends of mRNAs are modified. When we talked about RNA synthesis, we discussed how viral mRNAs produced from RNA genomes are polyadenylated. And that's summarized in this table, which summarizes how poly-A is added to RNAs produced from RNA or DNA genomes. And you can see that for the RNA viruses, the first two categories here, poly-A is added during mRNA synthesis by one of two ways, either by reiterative copying of short U's in the template. Influenza virus, for example, does that. Or by copying of a 5' U stretch in the template RNA, and that's what happens, for example, in picornavirus genomes. For DNA-dependent RNA synthesis or transcription, the addition of poly-A is different. For most of the viruses we will talk about, most of the DNA viruses, the poly-A is added after cleavage of pre-mRNA followed by polyadenylation. There's just one exception, and that is the pox viruses, which do it a very different way. They terminate transcription, and then they polyadenylate. So let's talk about how all these other viruses add poly-A stretches. Here's a schematic of how polyadenylation occurs on a DNA template for most viruses except pox viruses. We have at the top here is a mRNA in the process of being made. At its 3' end, now we're quite far from the 5' end of the mRNA here. The initiation would be far to the left. We're near the end of transcription. There is what's called a poly-A addition site. Near the end of transcription, the sequence is AAUAAA. This is recognized by a protein called CPSF, cleavage and polyadenylation specificity factor, which binds the poly-A addition site. And that leads to the recruitment of a number of other cellular proteins, which are shown here. And those eventually allow an enzyme called poly-A polymerase to be recruited to this site. When poly-A polymerase finally arrives, the mRNA, the pre-mRNA, is cleaved right downstream of the polyadenylation site. The cleavage product to the right here is eventually going to be degraded and thrown away. But now we have a 3'5' hydroxyl, and poly-A is slowly added to that by poly-A polymerase, this orange sphere. And here is the poly-A being added. Unfortunately, this poly-A sequence has become detached from the 3' end of the mRNA. It should not be floating off in space like that. That's an error that I've just picked up in the figure in the book. So poly-A polymerase adds A's slowly through the 3' end. And when enough A's have been added, they can then bind a cellular protein called poly-A binding protein. And as soon as PABP binds, then you get rapid polyadenylation, an addition of lots of A residues until you reach about 200, in which case the enzyme comes off and polyadenylation is complete. So an interesting process. You have transcription ongoing. Then in the process, while transcription is still continuing, the poly-A addition site is recognized, cleavage occurs, and then the poly-A is added. At the other end of the molecule of the mRNA, at the 5' end, is an unusual structure called the 5' cap structure. And this is illustrated chemically here. Here's the 5' cap beginning at the very 5' end of the mRNA, and it also includes some other bases as well. So as you know, the bases in RNA or DNA are linked in a 5' to 3' direction. That is, the 3' end of the 3' position of the ribose is joined by a phosphodiester bond to the 5' end of the next ribose moiety. The very 5' end of a capped mRNA is joined by a 5' to 5' linkage, as shown here. So the 5' methyl of this ribose is joined to the 5' methyl of the next ribose, instead of a 5 to 3' joining as is usual. In addition, there's not just one phosphodiester bond linking the 5', the most 5' base with the rest of the RNA, but there are 3. So we have an unusual linkage, a 5' to 5' linkage. In addition, some of the bases are methylated on this cap structure. So this position on the G, this is typically a guanine. So you have GPPP and then the next base. This nitrogen on the guanine is methylated. There is also a methylation on this oxygen of the ribose of the first base, and sometimes this ribose, the oxygen on the second ribose, is methylated as well. So cap1 structures involve methylation on the terminal G in the first base, and cap2, those two plus a third methylation site. So that's what a cap structure looks like, and as we'll talk about during translation, the cap structure is needed for efficient translation of mRNAs, and also their stability in other processes as well. The way the cap is added is different depending whether you are a cellular mRNA or a viral mRNA. And on the left is the cellular capping mechanism. You start with the 5' end of an mRNA, which is a triphosphate, and then the first base, then another phosphate in the second base, etc. A 5' triphosphatase removes the gamma phosphate, which is the terminal phosphate here. You're now left with a diphosphate at the end. Guanylyl transferase then adds GP to this RNA. So it removes 2 phosphates or pyrophosphate from GTP and adds the GP to the 5' end. And now you have your inverted linkage, the 5' to 5' linkage between this G and the next base. And then you have methylation, first of the G and then of the other 2 residues by cellular methyltransferases. This is different for viruses. Here's an example for the alpha virus capping mechanism. You have the 5' end of the RNA again with 3 phosphates. In this case, the GTP is first methylated, 2 phosphates are removed, and then it is added to the mRNA. So you can see that the order of events is slightly different. Capping occurs co-transcriptionally. Here at the top is our double-stranded DNA template. Here's the initiation site for transcription in the red arrow. Remember, when the RNA polymerase initiates, it begins moving down the template. After the initiation phase, we've passed the open complex and release from the promoter. So the RNA polymerase is moving down the template here, and it's making an mRNA. When the RNA polymerase has gone about 20 to 30 nucleotides down the template, the C-terminal domain is phosphorylated, the addition of 2 phosphates to this extension of the enzyme at the C-terminus. That signals for the capping enzyme, which is shown in yellow here, to come in and bind to the RNA polymerase and cap the 5' end of the growing mRNA. So you can see that capping occurs co-transcriptionally only after about 20 to 30 nucleotides of mRNA have been made, and the signal is phosphorylation of the RNA polymerase II.